Yeah, you. Satellite.
Like get like a research advisor.
Yeah. Under.
Yeah, good question. Personally, I was in undergrad. I'm a graduate.
About the solar.
So it's definitely a different situation.
Interesting now.
If you want to my email, maybe that would be good, and I can do some research on that. And
Yeah.
Ready to go. Yeah, just tell her to email me, and I will get rid of my information when I get. I'm Jules. Yeah. Ada, nice to meet you. Good luck.
Thank you.
I know. Well, then the question, yeah, I was question. I'm pretty sure we're right. I'm such a.
Alright.
I'm going to learn. Yeah.
Good. It should just be like just two change slides. Good. Downloading it now.
I confidently go off.
Yeah.
You can check, make sure you wanna make sure it's the right version of the slide with the,
Like,
Yeah.
I put in a new
I
version.
was like,
Kind of be a-
day and should be okay. You walk in the room and they like put up the. I don't know, it's like a PowerPoint of like what's the class fine. And I was like, what?
So this is what I saw.
It says, I'm on the study for the other one, I thought I was sitting like a few days.
I know, so there's not the right hand, it's just the right.
So we're all.
Okay.
You go to the last, you got your new
But
position.
it's like, well. I'm really prepared for that other.
Sure. Yeah, okay, perfect.
I think it's still big and pay, but.
But yeah, that's.
It was sad.
So on the geodetic one, I put the full to the PDF. Hopefully that's good enough.
You got the report.
Or would you like to put it?
We'll put it up here on the table.
Dave?
Alright.
Oh, my friend's showing though.
We do what we can to make it unique. So I. All right, you want me to go ahead and get started?
Yeah.
All right, thanks everyone for being here. If you don't know me, I am Brandon Jones, an associate professor in the aerospace engineering department. I started here at UT in January of 2016. I actually went to undergrad at UT, but I was math and physics, so I lived in this building during that time. But then I went to the dark side whenever I went to graduate school after working at NASA for 3.5 years. So I'm here to talk to you a little bit about CubeSats. So the idea of this presentation is that it's not a research presentation, it's more of an orientation. Inside of aerospace engineering, we think about CubeSats all the time. We kind of know a little bit more about what the state of the art is with CubeSats. We want to use this as an opportunity for those of you who are less familiar with them to see what is a CubeSat, where did it start, where is it now, what are the kind of missions that people are realizing with CubeSats right now, and then also give you an idea of what we're doing on campus with CubeSats. So that's kind of the overall goal here. So this just enumerates those same ideas. So yeah, we'll jump right in. So first of all, let's define what we mean by a CubeSat in our context. So here I've got just a spectrum of different masses and their classifications that you'll see for a satellite, where a large is greater than 1,000 kilograms, femtos down below 0.1 kilograms. So to give you an idea of scale, let's go back to the early days of space travel, where we've got Sputnik and Explorer 1. Those would be classified nowadays as a micro satellite, between 10 and 100 kilograms, right? Cut to some of the later missions, or maybe what was considered to be a small or a, we'll call it a feature lacking satellite with LEGIOS, which was classified as a mini satellite nowadays. So it'd be more 100 to 500 kilograms. But then for the longest time, when we were thinking of satellites, we thought large satellites. So here we've got a GPS bus. So this is out there allowing you to do your navigation. And then a big old geobird. And people describe these sometimes as being the size of a bus itself. So that, for the longest time, is what people have thought of for satellites. Now, New Horizons, which was an interplanetary mission that went off to Pluto, kind of backed off for reasons of the launch vehicle's capability and had considerably less mass and would be classified as a medium class satellite. But things are changing, right? So now we've got femto satellites. These do exist. I think they're a poster child for orbital debris personally, but from a hobbyist or the perspective of just how small can you make these things, you're getting to something that can fit in the palm of your hands. Now, this is probably the capability of Sputnik, and it's just beeping, but it has to start somewhere, right? So we've got femto satellites. We've got what is called a 1U CubeSat, and we'll talk about that in a moment, but that's a cube, 10 centimeters by 10 centimeters by 10 centimeters. And right there, it used to be the joke for the longest time, you weren't allowed to fly a CubeSat unless you had measuring tape on it. And the reason was that was what you used for an antenna. And then what is more common nowadays, which is a 3U CubeSat. So for those of you who are in the room right now, what I have right here, so that you can attach a size to it, this is the mass model for the Armadillo spacecraft. This is a 3U CubeSat. This was used for testing to understand the mass distribution of the object, but it's the same, except it doesn't have the solar panels on it. So to give you an idea, we're talking about satellites the size of a breadbox. Right? So that's the 3U CubeSat. So whenever we talk about small satellites, it's pretty much everything that's classified as mini or below. Okay, so small sats is anything inside of here. Now, a lot of times when people think small sats, they think CubeSats. It doesn't have to be a CubeSat. It doesn't even have to be the pocket cube that fits in the palm of your hand, right? Anything, at least according to NASA, that's mini or below is considered a small satellite. So we're primarily going to talk about CubeSats right now. And CubeSats, what was unique about them is that it created standards that if you adhere to it, you can launch from any CubeSat deployer. So what I have right here, again in the room, is an example of a 3U deployer. The idea is that no matter which company you are, unless you deviate from the standard, it's the same structure inside. And essentially, it's spring-loaded. And this is just a structure that we have, right? So you would put it in, if you've heard inside, there is a spring in there. It's usually much stronger than that. But it's got certain guide rails on the side, certain angles, certain structural specifications. After the lecture, if there's time, you're welcome to come and take a closer look. And it's got rails inside that control its orientation inside of that deployer. And then you would seal it up and it would deploy later on. There's a standard to that. And then they standardize not only the structural elements of it, but the size. Okay, there's a 1U CubeSat, which is 10 by 10 by 10, and then it builds up the 1U to a 2U to a 3U and so on. Okay, but it is a standard. You have to stick with that. I have seen some people get creative and say, oh, I can do a 6U, but I can break it apart as long as it fills the same volume. No, it's about being standard with the deployer. Uh-oh. I will allow it. Okay. We just had a minor technical difficulty in the room for those who are remote. So the idea is that the standardization allows for easy integration with a commercial rocket, and I'll have some illustrations of that here in a moment. But they even deploy these from the ISS quite often. Okay, whenever they go up and they do a resupply, they usually bring a deployer that will send so many satellites depending on the size of the deployer. So the history. Okay, the CubeSat standard itself, which was the 1U initially, dates back to essentially Cal Poly Pomona in collaboration with Stanford. The first launch of a CubeSat was in June 2003. They came up with the standard beforehand, it just took some time to secure the launch. And if you look at this, we've got a big, large GeoBus. And the idea was, Jordy and Bob, they noticed that in this area right here, there's not anything occupying that volume. You've got the big spacecraft, and then right here you've got what's known as the ESPA ring. This is where the spacecraft attaches to the rocket itself, and then eventually it deploys. But you, to save mass, you don't have a large ESPA ring, you make it as small as you can. And so it left some volume here. So what they said is, let's fill that volume with small satellites that can fill up that space. That was what they decided to do, where they started. And then from 1U, it grew and it grew and it grew. And one of the things that it allowed for this to do, their goal was to shift from the idea that to launch a satellite, you had to have this big thing, to education institutions could focus on this small satellite and learn how to build a satellite before someone goes work at Lockheed, Boeing, etc. So this is a video from the United Launch Alliance of a deployment. And I'll skip in a moment, but it just starts out with the launch itself. I think we all know what, if we watch SpaceX videos, we all know what that part looks like. So here, it's separated. This is the deployer for the CubeSats on the left. What you saw back there was essentially the bottom of the rocket being separated from the rest. What you're going to see in a moment is essentially the covering of the satellite, that launch fairing, is going to come into view. You know, they're starting to separate all the components so that they can launch the satellite and then launch the CubeSats. So there you see it flying off. And that's just half of it, right? And then in a moment, you're going to see the panels in that deployer on the left just pop open very quickly. And it's spring loaded. The satellite is going to shoot right out. And there's no explosives or attitude control or anything like that. It's just once that door opens, the spring activates, that potential energy becomes kinetic energy, and you've got your satellite deployed. Now, there are requirements. You cannot have your CubeSat powered on while you're there. So whenever the spring does force it out, it actually rips a small cord inside your satellite, and that's where your satellite starts to boot up. So there are things like this that kick it on, but it's off during that time. And then it's launched, and then you can begin your operations immediately after that, depending on what you're capable of doing for your satellite. So this is just giving you an idea of the launch trends of these small sats over since 1998, all the way up until now and projected into the future. So it's very niche for the longest time until about 2012, and we see things started to grow as it went further and further along. Now, cut to 2017, 2018, then we had a dip going into 2020. The 2020 dip is understandable, but then coming out of that, we've had a rapid growth in the number of satellites deployed. A lot of this is not just SpaceX. SpaceX does launch a lot of them, but this is also the rapid growth in the international community of launching these CubeSats. There are some instances where high schools have launched these 1U CubeSats, right? So if you got a really generous donator, you've got some donor, you got some 11th to 12th graders that have been involved in some of this stuff. Okay, and then projecting out, they're looking at even more in the coming years. In terms of what the use of these has been, right? Early on, you see the yellow on the top of these. It was very quickly identified that these could be used for technology demonstration and development. If you've got some low TRL technology, go ahead and launch it and test it in the environment. Figure out what works, what doesn't work, and you can iterate, and it's relatively cheap, right? So they did that early on, and that's where you see a lot of it in terms of education and technology development. But come to about 2013, 2014, 2015, this lighter blue Earth observation bar starts to grow. And that's thanks to Planet, which is a company we'll talk about here in a moment. And then communications, the darker bar, you see that's growing quite a bit more too. So it's transitioning from this idea of a small sat, a CubeSat, being useful only for education or for one-off technology experiments to being used in some operational fashion. You can use it for Earth observation, you can use it for communication. You've got some military cases, it's gone from this niche thing to almost a common mode that people, or a common technology that people use for spacefaring and technology development. So the idea, and I think this is a great way to put it in a nutshell. We've got the Cassini spacecraft, and students at University of Alaska Fairbanks, which is not known for being the go-to state for space, they're building these kinds of things on a regular basis. Right? They actually have a pretty good CubeSat lab there, and they're able to churn these out on a regular basis. So this epitomizes what this has kind of done, and some people say this democratizes access to space, because now you've got universities, high schools, et cetera, that can launch these up. But why a CubeSat? So what are the advantages, right? This, at least according to Allen Space, lists all the advantages of the CubeSat. So the first one is more accessible. They said to companies of all sizes. I'm just going to change that to universities for now. But it does make things more accessible. It's more affordable. The hardware in this, for what we did here, tops out at about $300K, compared to millions of dollars for a communication satellite. There's a big difference. You get down to 1U, and some universities have done it for less than $100K for the hardware. The launch at that point becomes more expensive than the satellite itself. Right? So it definitely becomes more affordable. Shorter development times. Just thinking about 9 months ago, I saw a presentation. I'm blanking on which university it was, but they went from concept to build to launch in 9 months. Right? You can do it really fast. Now they just did a 1U. They weren't doing anything complicated. They just wanted to prove that their university could do it, and they did. Right? Our missions that we're doing in the Texas Spacecraft Lab, we're looking more at the time scale of like 2, maybe 3 years. And a lot of the delay to 3 years is because of student turnover. I mean, students have to graduate, right? You train them, they do really well, and then they go and leave for better things. More up-to-date technology. You can constantly test the newest stuff, right? You don't have to be beholden to something that was proven at NASA 5 years ago after 15 years of technology development and laboratory testing. Smaller size and weight. That's an advantage and it's a disadvantage, right? I could carry this in by myself, and I even injured my foot this weekend, so I did it with a bum foot, right? I can do it without too much of a problem. Risk distribution. This is how SpaceX works, right? If you're worried about your satellite dying, well, just launch thousands of them. And then the economy of scale starts to take over and it starts to become cheap. More flexible services. Some people are experimenting with these and creating fully software-defined satellites as much as they can. You no longer need a radio that's purely hardware. You do software-defined radio, software-defined instruments. A lot of people are getting creative with what they're able to do. Independence and control. I don't have to go through NASA to build this, except to fund it, but that's a separate issue. Right? I could, if I've got the money, build my own satellite launcher. They argue greater data security. We don't worry about that in the spacecraft lab. And standing out from the competition, you can do that as well. Now, the disadvantages: size, weight, and power. Limited resources for instruments. To give you an idea, for our 3U CubeSat that Anand's going to talk about a little bit later on, we really want to put a GPU into it that is nothing in a desktop computer. It blew the electrical budget wide open, and we're having to revisit some other things. Just that small little change then said, okay, now we got to look at larger batteries. Oh, that means a change to the mass properties. Oh, larger batteries means we've got to fill up the volume, and so on and so forth. Right? You're very constrained in this type of environment where you're fitting everything into the size of a bread box. So limited scopes and capabilities. Whenever it comes to these small sats, simple is the way to go. You're not creating one mission that does 20 different missions or studies. You're really creating a satellite that does one, maybe two studies. And you're maybe making up for depth with breadth, right? I could launch 8 of these and get better temporal resolution of the Earth than launching one with a hyper pristine, precise instrument, and then only getting information every 14 days over a particular region of the Earth. No redundancy. There are many single points of failure in these things. So if it dies, it goes. And there's a reason that last I saw, over 50% of CubeSats don't work. Right? Because one thing goes wrong and the whole thing may go bad. Because you don't have the swap, the size, weight, and power to be able to handle that redundancy and recover from those issues. And then the other thing is launch-specific limitations. The CubeSat standard gives you an idea of what the size, shape, maximum mass, etc. for the CubeSat will have to be. But we don't get to go in there and say, SpaceX, I want to be launched into an orbit with this inclination and this altitude. They'll laugh at you unless you're willing to pay for the whole thing, right? You're kind of stuck with whatever the primary launch was and where you can get that mass on board. So you have to be flexible. And then each launch provider also has different requirements in terms of the testing of the vehicle. They may require a different vibration test profile for SpaceX versus Rocket Lab versus Firefly, right? So you kind of have to be nimble for these potential changes. So I wanted to talk about some science concepts, some recent missions to give you an idea of what people are currently doing with CubeSats. So if I recall, this is the only historic one I have in here, but it is a small sat, not a CubeSat. But the Cygnus mission, which was out of SWIRI down in San Antonio, was a series of these small satellites built and tested down in San Antonio that were for science and weather monitoring. Right, so this was an early example of a success with these small satellites, that they were able to do something that at the time large satellites were not able to do, just due to their temporal resolution of having multiple satellites deployed. And I mentioned Planet. Now, Planet is building these 3U CubeSats kind of almost on an assembly line. What are they doing? They looked at what, at the time, Digital Globe was doing with Earth imaging, and they said, let's do better. But they didn't want to do it through resolution. They knew they couldn't beat Digital Globe's photos, which were used for Google Maps for the longest time. They knew they couldn't do that, or they didn't have any competitive advantage over that. So what they did was said, instead of 3 satellites, let's have a flock, and they named it, their constellation, the flock of Dove satellites, where they have over 100 of them operating. And the idea is, through these 100 satellites, they can revisit certain regions of the Earth, sometimes as frequently as on a daily basis. So they can get an image, wait a day, they can get an updated image, and so on and so forth. Right? So they get that better temporal resolution, which is an improvement when you care about what happened day to day to day. Right, this could have some disaster relief implications, it could have some DoD implications, there are many things that they could do with this. And they, at one point, had the record for the largest number of satellites deployed all at once, when they deployed 98 of them on an Indian rocket in around 2010. Okay, so they still operate that constellation today. Now, when people think of the proliferation of these small sats, they think of SpaceX and Starlink. They are operating over 1,000 of these. They've launched more than 1,000, but not all of them are still operating, right? Now, this does create some challenges for astronomers. SpaceX has tried to react positively. Now, how successful they are, I'm talking to the wrong cloud. I'm not going to lecture you on that subject. But you can see in terms of the orbit debris environment, these strings of satellites, like what you see over the Pacific Ocean right there, these are the SpaceX satellites, right? And you can see it visually in the debris field. Now, on one hand, on the science side here at UT, you hear about some of the disadvantages, but whenever I visit my wife's family in northern Minnesota, they all use Starlink. You know, it is, suddenly they have internet that works. You know, they love it. You know, so it has, absolutely, it has its positives. Some people love it and are able to do some amazing things with it. Now, one thing to note is that the Starlink V1 satellites were classified as small sats. V2 and beyond are not small sats. So they have allowed for the size, the mass of the vehicle to grow over time as they prove the feasibility and taking care of some of the issues with operating these satellites, right? So I still included here because the V1s are small sats, but they've actually grown outside of that classification. So I thought this was really cool when this happened. This was the first deep space CubeSat, Marco A and B. So the idea is that the InSight Mars land rover, as it was transferring from Earth to Mars, it deployed these two 6U CubeSats. They were already on the same trajectory, and they became communication relays for the landing. So they didn't have to worry about one of the other Mars spacecraft being in a particular spot to relay data from the lander back to Earth. They had these CubeSats in a similar orbit along a trajectory that would allow for them to be that relay, right? And to my knowledge, this is also the first image of a planet with human hardware shown in the back, in the same image from orbit. Okay, it's just kind of cool from my perspective to see that. You're so used to thinking of a rover in what looks like a red desert, but in this case, you see Mars with human hardware in the background. I thought that was really cool. But they showed that they could do this. It had some significance and some use beyond Earth orbit or as a toy, right? And then they, rightfully so, won 2019 Small Satellite Mission of the Year. So what I did for the following is I wanted to highlight some of the other Small Satellite Mission of the Year awardees to give you an idea of what the community is saying is pushing the boundary. So the next one is Capstone. If you're not familiar with Capstone, it is a 12U CubeSat launched by Advanced Space with NASA. They use Terran Orbital, which is a company that builds CubeSats. They built the bus for them. Advanced Space did all the mission design, came up with the needs, goals, and objectives, the technology that needed to be developed, etc. Terran Orbital built it, and this should be 9.2 in our Joe, apologies. They wanted to use this to demonstrate or to test and verify what the environment would be for the NASA Gateway station. So in the image on the bottom right, it'll start over here in a moment. We've got the launch from the Earth out on what is known as a BLT, a ballistic lunar transfer. It's pretty much going out close to the sun. The sun gives it an increase in the energy in the trajectory, and it comes back in, comes close to the moon, and then it is captured by the moon. If you look up in the image at the top, you see right there, those 4 nozzles, it did have low thrust capabilities. Okay, so it did have its own thrust. So one thing to note is that once it's in this BLT, it is not on some other vehicle. It's not piggybacking. That is the CubeSat itself. The CubeSat is doing that transfer, doing all the trajectory correction maneuvers, coming in, slowing down around the moon, etc. Now, partially because I know the folks that launched this, I was roommates with their chief technologist once upon a time. They are actually very, very glad and thankful that they had to do this ballistic lunar transfer. So why is that? Because CubeSats don't always work the way you expect them the first time. So what if you launch direct from the Earth to the moon, you're doing a 3-day transfer, right? They would have failed if they had done that because they had a thruster that failed and didn't work. One of those 4 thrusters. So they were down to 3. And then they also ran into an issue where they accidentally almost froze the fuel tank. So to identify these issues, debug it, and fix it took about 2 weeks. This trajectory, you know, that they launched in June and arrived the following November, that gave them time to debug it and to figure out the problem. It would not have been successful if they went for the direct transfer, right? So since they've been there, they have had multiple studies for autonomous navigation. They demonstrated that you could operate in the 9.2 in RHO. They developed new algorithms and demonstrated they work that could be used by NASA for the Gateway program. And they showed that these CubeSats can be used in that kind of environment. Licia Cube was a part of the NASA DART mission. It kind of followed the same model as Marco A and Marco B, in that it piggybacked along with DART. And part of the way, as DART was coming in for its impact, it ejected this CubeSat out of the back. And then it turned on and started recording as the main DART mission went and hit Dimorphos. Okay, so it got the images of the impact. And then that CubeSat stuck around in the vicinity and did the scientific studies of the asteroids, got improved orbit determination data to understand the effect of the impact on the orbit of Dimorphos about Didymos. And it contributed actively to the science in that case. And it would not have been able to get the level of precision in their measurements without that. Now, if you're wondering, why is he focusing on interplanetary? The winner in 2024 was an Earth mission, an Earth observing mission. So this actually came out of the MIT Portugal program. There is a UT Portugal program, but the MIT Portugal program, they had a satellite called Eros MH1. This was a 3U CubeSat, and it used a software-defined radio along with some sensing instrumentation to monitor the water off the coast of Portugal. So they had a very focused mission, but what they wanted to do with their sensing in a 3U form factor really pushed the boundaries of what they could do with the size, weight, and power constraints that they had. So they did use the hyperspectral camera. They were tracking tagged marine life. They won the satellite mission of the year because of the amount of science that they were able to do in that small form factor. So these missions that are winning are not just the ones going beyond the Earth. It's also pushing the boundaries of what you can do with science. So this is the NASA smallsat CubeSat fleet in 2017. This is what it is today. The use within NASA has grown very rapidly, right? This is its use. I won't say it has no bounds, but people are noticing more and more the potential uses for it for technology demonstration, science, augmenting other missions, etc. So this is just growing rapidly. One of these days we'll get our mission on there here pretty soon. I'll let Anand talk about that mission in a moment. So with the remaining time, I wanted to talk about the Texas Spacecraft Lab and what we do at UT, give you an overview of what the laboratory is doing. And then I got one of my graduate students here who is going to talk briefly about our current mission and let you know about the project that is joyfully eating up all our time, right? So the Texas Spacecraft Lab, I did not create it. It existed before I started at UT. It started in 2002. Professor Glenn Lightsey spun it out of his space dynamics laboratory here on campus. And it became more of the education arm of the work that he was doing at the time. He went on to other things. I am actually the 4th director of the laboratory in its lifetime. I've been in charge of it since about 2019. The students like to say it's a student-driven laboratory. They do all of the hard work. I was originally told, don't let them break ITAR rules. And that was the directive I got from the department. And so far, they haven't, I think. So what do we do in that lab? We focus on the design, manufacturing, and operation of small satellites. It's a lab that's really designed for the students to learn about systems engineering, learn about the nuances and the challenges whenever you have a small swap type vehicle, and then for them to butt their heads against the challenges before they go out into industry and they need to do the same thing. Right? So we are government funded in the sense of we've had funding from the Air Force Research Laboratory and funding from NASA. Our big project right now is NASA. The AFRL money was through the University Nanosatellite Program, which is the DoD and Air Force Office of Scientific Research's baby, in that it was created to start training universities to use small sats to then enter the workforce. So they held competitions every 2 years. UT has competed in a couple of them. We decided to sit out this latest round so we can focus on some of the work we have currently. In terms of the demographics, it's not just aerospace. Okay, it's broken down by projects here. We'll talk about scope. TMA, it was technology market assessment. That project is now React. We've got a small weather balloon team, and then we used to have a team called Vision. So you can see most of our work is really on scope that we'll talk about. But for the major breakdown, about 1/3 of the lab is aerospace engineering. But then we have a large contingent of ECE, ME, we've got some physics and astronomy, computational engineering, computer science, and we have 1 finance student. And we did not put them in charge of the budget. They just wanted to come in and help out with management of the lab. They wanted to learn that, right? So we do have 1 finance student. In terms of the breakdown with freshman, sophomore, junior, senior, we're more or less evenly distributed. We don't have as many freshmen, but part of that is freshman year is an important transition time. So we are a little more cautious of bringing on freshmen in the fall semesters, but we have created some on-ramps to do that within the lab, where it's maybe a less technically challenging, less stressful project, but they learn the systems engineering and about their subsystems so that they can then jump on to scope or React later on.
How many students is this?
Oh, okay, so we don't have the exact numbers. This is the typical demographics. Right now, it is at about 40 because we had a good number graduate. They're going through their recruitment cycle right now. So if you know of any undergraduates who really want to learn a bit more about satellites, I mean, we got finance, we've got physics, astronomy, let them know. We welcome graduate students as well, but we tend to be more undergrad focused. So in terms of PAT's missions, it all started with the Vivo 1 satellite, which was just a 1U CubeSat, right? This is during the Glenn Lightsey era. There's big success story from the early 2000s was Fast Track. So it was a small satellite. It was these 2 hexagonal satellites put on top of each other. It was a small sat. It's separated, and then they did proximity operations near each other and proved that you could do that in this kind of form factor. Okay. Then there was the Race 3U CubeSat. It would have been awesome, but the launch vehicle blew up on the way up. And then there have been some other deployments from the ISS with the Vivo 2 satellite. Vivo 2 was attached to, I think it was AggieSat 6. They both deployed together, and the idea was they would separate and then they could repeat the fast track mission, but they never separated. And they unfortunately designed it such that the antenna for each was inside of the other satellite. So since they never separated, they were never able to establish communications. So we're gonna take a little bit of a aside. For a project that we got funding for. Starting conveniently in July 2020, which is a great time to start a brand new project. For crater-based navigation and timing. So NASA wants to do autonomous PNT near the moon, but they don't want to do ground-based monitoring of satellites at all times. And they have a concept that they call LunaNet, for populating the region around the moon with many small satellites that all serve as nodes for communication, navigation, and timing. So part of the call was just to come up with PNT solutions. So we took an idea from the constellation program in the 2000s and said, let's use craters on the moon at similar to how the maritime community uses lighthouses to navigate our spacecraft. Okay. Now we want to do this on a CubeSat, and the challenge there is the CPU. And Anya will speak a little bit more to some of the solutions on that here in a moment. This project was successful. We were over the 2.5 years that we worked on it. We showed that the algorithms we developed could run on CubeSat compatible hardware. We were able to do navigation with the algorithms, all the timing. We met all of our benchmarks. NASA said, we like it, but we're not going to pay for you to go to the moon to demonstrate it. So we came up with a compromise. So what we're doing instead is we are going to be in Earth orbit, and we are going to detect archipelagos, islands. Now, it's more difficult than the crater case because we have weather to deal with. So we're going to make up for the challenges with weather with just the number of times we can run the experiment. But the idea is we're in low Earth orbit, operating for about a year, snapping photos of islands as we're passing over them. And we're using those in the exact same algorithms that we would do for the crater navigation and timing, except we change the detector. The neural network-based detector has to be swapped out. And NASA was okay with that. So that is the spacecraft for optical-based position estimation-1, or scope 1. We added the -1 because NASA made us. We couldn't have a simple name. We hope that there's a scope 2, but sometimes I get the question, what about scope 2? We're hoping. Right? So we are taking the same idea with the crater nav and timing, and we are doing this in Earth orbit with islands. The idea ultimately is to raise the TRL, technology readiness level, of these algorithms up to TRL 7 through 9, depending on how you interpret those algorithms, but to demonstrate it in situ on board with data gathered from that environment. So with that, I could talk more about it, but I'm just going to let my graduate student who does all the hard work speak more about scope. So this is Anand Agarwal. He's a PhD student co-advised by Dr. Maruthi Akella and me in the Aerospace Engineering Department. And I'll let you take it away.
Okay, yeah, so I do a lot of the detection side of the pairing of the algorithms that we're going to discuss. So islands as landmarks. So what we have on the right here is a distribution of islands on the Earth. Now they're mainly concentrated along the continental coastlines, but there are some pockets where running this experiment might be a good idea. Southeast Asia, also off the coast of Australia and in Polynesia. So the reason why islands are such great landmarks is that there's a clear distinction between the island itself and the background, being water. One thing that we have to, kind of mitigate against is that islands can be, they're non-convex by nature, right? So you could have, I'll show an example where it kind of looks like the center of mass, if you were to draw a box around it, would be outside. And we have a large scale. So the largest island on Earth is Greenland, but we can get geode areas down smaller than a kilometer squared. And one thing that we will have to mitigate against that we don't have on the Earth, or we don't have on the moon, is atmospheric effects. So clouds, and one approach we can do to kind of mitigate that is a domain randomization approach. We just hope we provide enough training images for the detector to get used to what a cloud looks like. And basically consider it as background class. We could make some modifications so that We could also try to directly detect the cloud itself, but that would be a little bit more complicated based on what setup we have. So part of this detection side of things is also figuring out what are the right camera parameters. So the island catalog we use is called the USGS Big Island Catalog. So those islands range from 1 kilometer squared in geode area to Greenland, essentially, which is about 2 million kilometers squared. And the cameras that we're looking at are pixel resolutions around 2,000 pixels squared, so 2,000 image height width, and then the focal lengths of the lens that we're looking at are around 70 to about 4.8, something like that. And basically what's happening is our field of view is decreasing, and then what that effect has is that the ability to do the detection, how big the island is on the pixel in pixel space on the image is changing. So we part of designing the mission was kind of finding a camera that would best suit our needs, and so we haven't really selected the focal length, but we have selected the SpectraCam, which is a red wire camera, and it has a higher spatial resolution than the Gecko imager. But the idea is that we want to make our camera. We're basically doing a trade between our detection capability and what we can see. And basically we want to be in this area. Now, as we get closer and closer to the left on the x-axis, we're getting smaller and smaller islands. So I kind of wanted to show you what this looks like, so what we're trying to do. So this is an animation of a field of view, and this field of view is 4.8 millimeters. So the lens that it's attached to is a 4.8 millimeter focal length lens. And the yellow, hopefully you can see it, is what is visible in this geodetic polygon. And I think it's black. When black dots come up in that polygon, that means these are detectable. So we came up with a heuristic for what we consider detectable, and that's based on the detector itself. Yeah, so when we are in this area, we're hoping to run the experiment at a high frequency. And this is just a visualization of tracks where the experiment could be run. So on the left-hand side, those little purple streaks, those would be continuous time steps of multiple islands that we wanted that could be detected. So this is a visualization of what's going on with the entire system. So on the top left, this is where we do the training. So we take our real imagery, we segment that imagery into the corresponding islands. And the way we do that is we use the water mask. And that is collected from a lot of Earth observing satellites. I'll go into that in the next slide. But basically what we're trying to do is detect and regress that mass. So the outline of the island. And so what we would, to actually run this, we take an input image. And this is based off of this is based off the field of view that we've selected. So in this example, it's 16 millimeter field of view with our specific camera. And we're pulling this image against, if you know what Sentinel-2 is, or the observing satellite Sentinel-2, we're pulling it against a catalog. And then, so we'll send it into our neural network, and we'll get out these detected mass. And then what we do is we calculate the center of mass of the mass. It's a binary mass, so it's just the standard center of mass equation. And we can project that back onto the image. And so these are our detected centroids. And the next step is we have a prior estimate of where we are. And we use this prior estimate, this RECEF, to localize the catalog. So we have this spatial catalog of the Earth's islands, and we use that prior to basically build a subset. And we use that subset is then projected into the pixel space. And so we get these identified craters, or we get the catalog craters. And then we do an identification step, and that does the matching. And we use the matching information in our measurement model to update our prior estimate. And this is basically the manifestation of basically the detection side of things is a measurement model that feeds a Kalman filter. And that's our physics-based estimation model. So the way we build this training data is we will take the island catalog and we will basically build a set of bounding boxes in geodetic space that encompasses the islands, and sometimes we expand it and that'll bring in more islands. And this also serves a purpose to make the island robust to multiple detections. There's a corresponding water mask, and the way this is generally generated is a lot of these Earth observing satellites have they're either multi or hyperspectral imagers, and they have an infrared band, and they compute a normalized I think it's normalized water difference index, and we can use that to basically build our process mass. So we take this water mask, the corresponding water mask, and it's 1-to-1 in the polygon. So meaning like what we're seeing, and when we pull in here, it's going to be an exact match to what the water mask is. We will run it against some Python processing to basically fill in holes, and then we do connected components to get the outline. So we will, these are basically, this is our training data right here. This is the process mass. This is our truth labeling, and that's the image input. This is an example of projecting that information back on the truth. And what we're trying to do is basically regress the shapes, the outlines of these shapes. Yeah, so we pull from the Copernicus Space Ecosystem. It is a data platform hosted by the European Space Agency, and it's free to basically extract this image. And it's mainly right now it's mainly Sentinel-2. And then another thing is we are in this step, this part of the process, we're only using what we call global quarterly mosaics, and basically that means the atmospheric effects have been filtered out. And yeah, so once we have this this outline, we will compute a center of mass of the detected binary mass. And that'll give us a centroid. So this is an example of like basically running up all the way to the ID step. So in the top left, so this is the island Okinawa. In the top left, we have the truth contours in red, the truth centroids of where the island should be, the island center of mass should be, and then also in the maroonish colors, the bounding box of the island. This is what the truth mass looks like once we've done the processing, and this is what the detected mass looks like. This is just a binary. This is a colored mass, and this is binary mass. And then we'll process and calculate the center of mass of each of those detected masks. And then we'll do the identification step. And in gray, this is where we have a match. And the yellow denotes, between the gray circles, denotes the distance. This is just to visualize it. And this is a blown up high contrast image of what that looks like. And key here is that we've localized the island catalog with the physics brace prior. And then the actual matching portion, we set up an optimization problem, and we use the Munkers algorithm and the optimal subpattern assignment metric to basically calculate the distance, to calculate the cost. Okay, so this leads us all the way up to right here. So once we go right here, we send it into this measurement model, and this portion of the estimation is being handled by another partner, Dr. Zanetti, and his graduate students. But yeah, that's kind of the payload navigation system overview. Any questions?
Yeah, so we got there is a class after us, so we got a little time for questions, but we want to make sure we vacate.
So, like in this specific application, what would you say are your limiting factors for this in terms of sensors,
Yeah.
compute power, which is also kind of compute, I guess,
Right.
in terms of like, do you sense, can you win by adding sensors? Do you need less compute, or is compute beating? I mean, the thought that occurred to me as a astronomer is stick a star tracker on the other side, and you get extra information, but that's mass.
Yeah.
So where are the optimization, I guess, directions?
So right now this runs in a similar like edge device. So this edge device that we ran it on, we were able to achieve per image about 2 seconds worth of inference, or it took about 2 seconds to do the inference. We were gonna try to make that way quicker. That is the main bottleneck, and that process is quite power hub heavy too.
So it's limiting on the power. We do have a star tracker because this algorithm requires us to know our attitude.
Yeah,
So we do have that star tracker, but yeah, we're running into potential challenges with the power. And it doesn't help that our ADCS system required us to remove another solar panel 3 weeks ago.
Oh.
You know, but I mean, these are little solar panels, you know, but I wish it were a zero sum game. Sometimes it feels like it's a negative sum game, but we're running into power issues right now.
yeah. The star tracker is used in this portion because most of the math in here is done in Earth-centered inertial, so we need to be able to convert back from Earth-centered inertial to Earth-centered fixed. We also need to know how good we are native pointing.
You've got an online question from Sid.
Okay, I can pull it up. Yeah.
Can you guys hear me?
Yeah, go ahead.
Yeah, thanks. This is a really interesting talk. It's great to hear what's happening in some of the other areas for CubeSats. I'm going to break a fundamental rule and give a comment instead of a question. But I just wanted to tell Adam that if he wants to think about this in terms of astronomy, CU is developing a 12U CubeSat called Sprite that's going to have equivalent sensitivity to a mission that was a mid-scale explorer that launched in 1999. So just with advances in grading, quantum efficiency, and coding improvements, throughput, we're actually able to launch in these small CubeSats things that are competitive with mid-scale technologies from a generation ago.
So you mentioned that the islands are non-convex. Was there like some benefit or downside to craters being convex?
Yeah, you can use analytical techniques to characterize them. So you can fit them to an ellipse.
Once you detect the pixels, then you fit into an ellipse, yeah. Whereas here, very few islands are elliptical. It's a problem. Yeah, so we're more sensitive to errors in that detected contour than with the craters.
Yeah, and also
Almost a follow-up on that. So your part of the crater counting thing was to have the exact pattern of craters as part of the identification. Is that correct?
Oh, so that is a way to do it. So they use that in what is called the lost in space problem. Lost in space problem is I don't know where I am. Now I get an image. I got to figure out where I am. That's a harder problem. NASA was okay with us not trying to tackle that.
Okay.
So Anand had said that we have some knowledge of prior.
Yes.
And we've got the attitude from the star tracker. We have some estimate of where we're pointing, and we can reduce the list of possible craters or islands to what we expect to be in the field of view.
but we are in a research context, we're gonna try.
Yes. Understood. Questions?
Only one last check online. No more there.
A more general question, I mean, when you talk about femto satellites, to your point about that being a synonym for space debris, like how many things up there are like trackable, and are we reaching the point where like someone can put something out and we can't actually track it from the ground and even know if it's a problem?
Good question.
And how well can we fix that?
Yeah, so good question. So for these satellites in LEO, they can be tracked. These 3Us and even a 1U in LEO could be tracked. Go out to GEO and they cannot, but the FCC, and we are getting to reap the rewards of that, is that if you want to call it that, in order to get a communication license, if you're going to be in LEO, you have to show you're going to re-enter within 5 years after your end of mission.
Okay.
And then going beyond that to GEO, et cetera, they have other concerns on how they're going to take that. So the community is cognizant of this. And you kind of have to make your vehicle tractable. Or it has to re-enter if you're below everything else within a certain time period.
And so far as everyone following that, I mean, the US government only has so much reach. I guess.
Yes, so our original launch was going to be with the NASA CubeSat Launch Initiative, CSLI. They are having budget issues. But their requirement to us was you got to follow this 5-year goal. You have to show that you're going to re-enter. So for example, NASA, if they were going to send you up, you had to show that you were going to be consistent with that requirement. But that is a US requirement. Europe is ahead of the US when it comes to this kind of stuff. Some countries are behind.
Well, thanks very
All
much.
right, so I'm part of what you're.